this section, I will give one more example on plastic, hinge by hinge analysis. Now we consider a structure, bow and a fixed end beam under concentrated load. So let's see here, the beam is AC, a fixed end beam, and the concentrated load is located at 1/3. At 1/3, not at the middle, but at 1/3. The load is P, and the total length of the beam is L. Okay, it is both fixed and beam. Now, elastic phase. Can you plot the moment diagram of this structure? I will give you maybe 1 or 2 minutes. Try to plot the moment diagram of this structure. So in this class, I assume that you already learned about the applied mechanics. So I assume you are able to plot any you can plot the moment diagram of any type of structure. So especially indeterminate system. So determinate system is simple. I think every student can plot moment diagram very easily, but for indeterminate system, it is a little bit different. So you have to, if you forget, please back to the applied mechanics and learn how to plot the moment diagram and how to calculate the deflection of the structure. For example, can you determine the deflection, the maximum deflection here? So what is theta equal to what? So I assume you can plot, you can calculate, you can determine the deflection and the moment diagram also. Okay. So for example, in this case, the moment diagram can be plotted like this. Is this right? So a little bit wrong because the big one may be here, this section, and the second value is here, and the lowest is here, right? And what is value? What is value? So you have to know how to plot. Okay. In this case, in elastic phase, we have this moment diagram of the given structure. So here, this is 4/27 PL. Here is 8/81 PL, and here is 2/27 PL. So the big git moment is here, and the second, the middle, is here, and the lowest, the smallest, is here. So what does it mean? It means if the hinge plus hinge occur here first, okay, so plus hinge occur here first, and then if the load is increased, then the second hinge the first hinge here, first hinge here, and the second hinge will be occur here, and the last hinge will be occur here. So 1 and 2 and 3. The first one and first and second and third hinge. That is procedure. Okay, so to solve these problems, we will use superposition method. Do you remember superposition method? So I assume you also understand, know superposition method. Okay, and in this example, we will use superposition method and TenTeP approach method. TenTeP approach. So we combine between the superposition method and TenTeP approach to solve this problem. Okay, it is normally used for highly redundant structure. Okay, let's go. Let's go. In elastic limit, as we already mentioned, the hinge occur firstly here. So let's say MP equal to 4/27 P1L. P1 corresponding to elastic limit. Okay, so in this case we have P1. So MP equal to 4/27 P1L. And here at this section we have 0.67 MP. We can calculate, right? We can calculate. And at this section, this value equal to 0.5 MP. If this is MP, then this is 0.667 MP. And this section, the moment of this section is 0.5 MP. Again, MP equal to 4/27 MP P1 L, this one. And from here we have P1 equal to 6.75 MP over L. Okay, this is elastic limit load. Elastic limit load. So please remember this value MP, and here is 0.667 MP, and this section is 0.5 MP. Okay, because we will use this one and superposition method to solve the next step. And the deflection, the maximum deflection here due to P1 is θ1. So the deflection here, θ1 equal to this. So as I mentioned, I assume you understand this one. This is the result of applied mechanics. So please check. So to determine the moment diagram as well as the deflection of the given structure, let's say the indeterminate structure, we can use load method or deflection method, or we can use the given table, given diagram. So please check in the applied mechanics. Okay, so I assume you understand this one. Deflection equal to 8/2187 EI, but finally equal to this one. Okay, so now at the elastic limit we have P1 equal to this, and deflection then so on equal to this. This is function of MP. Okay, function of MP. Next step, when P is increased, return P1. Okay, P is increased, return P1. Now we will use the TenTeP approach So TenTeP equal to P1 minus P. Okay, P1 minus P. P1 minus P equal to TenTeP. So because we assume this section is ill, so it is hinge, but because of plastic hinge, so we just use TenTeP. And now the structure becomes one hinge and one fixed and beam. The original one is fixed and beam, both fixed and beam, but now because of the first hinge, then we have one hinge and one fixed and beam. And due to TenTeP, then the moment here is 14/81 TenTeP L due to TenTeP. And the moment here for this structure, okay, for this structure is here due to TenTeP, okay, and now structure is changed due to the first hinge. So remember, this is due to TenTeP and the first hinge, and remember the original structure and original moment diagram. Next step. Now P2 equal to P1 plus TenTeP for P2 equal to P1 plus TenTeP. P1 plus TenTeP equal to this diagram of P1 plus TenTeP. It is result of superposition. Okay, so let's say this section is MP. It remain MP. It is plastic moment, and the moment here at this section equal to MP. It is second hinge, first hinge and second hinge. This is equal to this part. This part is due to P, due to P1, due to P1 of original structure, and this part due to TenTeP of the second hinge, the first hinge structure, first hinge structure. Okay, so again, this part is due to the P1, and this part due to TenTeP of this structure. Then we use superposition method. Then we have the moment here equal to this plus this one equal to MP for the second hinge. So second hinge will be occur here as we already mentioned. And how is deflection here? How is deflection here? Let's think about that. Okay, so from here, this equation now we have TenTeP. We can calculate TenTeP corresponding to the second hinge. Okay. Now we have TenTeP equal to 1.927 MP over L. Because we use this equation, okay, then we have TenTeP. TenTeP now is corresponding to second hinge. Okay, so let's say P2 is the plastic load correspond to second hinge. P1 is for first hinge. P2 corresponding to second hinge. P2 equal to P1 plus TenTeP. So P1 is the first hinge and TenTeP, and TenTeP equal to 1.927 P over L. And what is the moment here? Moment here also equal to this part due to P1 and this part due to TenTeP. And by using superposition, and we have moment of the section is 0.786 MP, smaller than MP, so it's not hinged at all at this step. And because due to MP delta P, then we have deflection equal to this one. So this deflection, okay, this deflection. So this deflection due to the structure after first hinge, okay, after first hinge, and equal to this, and equal to this one. So now we have tentative, I mean the total deflection equal to the deflection due to the P1 and deflection due to TenTeP equal to this one. Okay. So now we have TenTeP, or because we have P1 and TenTeP here, then we can calculate P2. P2 equal to P1 plus TenTeP, and deflection TenTeP equal to this. Next, P greater than P2. Now continue to use TenTeP approach. Okay. Now TenTeP equal to P2 minus P. Okay, minus P. Sorry, P minus P2. P minus P2. Mistake. Okay. P minus P2. So P greater than P2. So let's say okay, TenTeP equal to P minus P2. Then the structure now is cantilever beam, okay, because the first hinge and second hinge. Then we have now is cantilever beam. Then the moment diagram of the cantilever beam due to TenTeP is TenTeP 2/3 of L. Very simple. You already know this one, right? It is in a determinate system, so very easy to determine the moment here. Okay, due to TenTeP, moment here now is not increased anymore, and here also. So here is MP and MP, and just as increment of the moment here at this section. So now we have P3 equal to PP. PP equal to P2 plus TenTeP. Okay, plus P2 plus TenTeP. That is called PP, plastic load, a total plastic load. So at this case, we have first hinge and the second hinge, and PP corresponding to the third hinge, and then we call collapse load. Collapse load. Okay, collapse load. So we already have MP here and MP here, first hinge and second hinge, and what is the third hinge? What is value here? We have moment here is MP because the last hinge equal to this one due to P1. Sorry, P2. Okay, due to P2, and this one due to TenTeP. It is cantilever beam I already mentioned. Okay, so P2 due to P2, moment due to P2 plus moment due to TenTeP equal to moment here at this section. And moment here now equal to MP. We assume it is third hinge. So from this equation, we can determine TenTeP now. New TenTeP. TenTeP equal to 0.33 MP over L. From this equation, we can calculate MP as a function of P and L. Okay, very simple. And deflection due to TenTeP. Deflection due to TenTeP equal to this one. This is a reflection of cantilever beam. Okay, deflection of cantilever beam. Then it's simple. You can understand this. Or equal to this one. Or the total deflection corresponding to P3, and P3 and delta 3 is total deflection at this point equal to delta 2 plus delta P. Delta P is deflection due to here. Then it is equal to this one, or equal to this one. Okay, then we have delta P or PP, P3. P3 equal to P2 and plus delta P here. Then we can calculate P2. P2 means PP, plastic load. Okay, plastic load. And we have the corresponding deflection. Delta 3 equal to this value. Okay, so we can sum up by drawing the load deflection curve. Okay, load deflection curve. This part is elastic phase, and at this point, it is corresponding to initial ending plastic limit load. Okay, plastic limit load. In plastic limit load, P1 equal to 6.75 MP over L, and the corresponding deflection delta 1 equal to 0.0247 multiplied by P MP L square over EI. And this part is elastic plastic of first. So this is first hinge, and the second hinge occur here, second hinge. Then the load correspond to second hinge is P2. P2 equal to 8.67 multiplied by MP over L. And the corresponding to deflection delta 2 equal to 0.0423 multiplied by this one. And this point corresponding to third hinge. So it is first hinge, it is second hinge, and it is third hinge. The third hinge corresponding to third hinge, we have structure like this. So first hinge here and the second hinge here corresponding to this point, and the last hinge here corresponding to this, and P3 equal to 9 multiplied by this one, and the deflection is here, total deflection. So we can plot the force deflection curve. Okay. Okay, so the homework of this week is only one problem. So please do problem 1.12 in the textbook. Okay, 1.12 in the textbook. Okay, see you.